Hello everyone, welcome to Deep Sleep Global Academy. And tonight we are going to explore something beautiful, something that holds the key to understanding all of matter, the periodic table. You might be studying for competitive examinations, or maybe you just want to understand the world a little better. Whatever brought you here, you are in the right place. Before we begin, I want you to know something important. You don't need to remember everything tonight. This video is designed to be listened to again and again. While you study, while you rest, while you sleep. Each time you listen, your mind will absorb a little more. Like water soaking into soil, slowly, naturally. So get comfortable. Dim the lights if you can. Let your breathing slow down. And let's begin this gentle journey together. The periodic table is not just a chart on a classroom wall. It's a map of everything. Every element that makes up our universe, organized with perfect order. And tonight, we will walk through that map slowly, calmly, together. Let's begin. Imagine you're standing in a vast library, thousands of books everywhere. No order, no system. You need to find one specific book. But where do you even start? This was the problem chemists faced 200 years ago. By the 1800s, scientists had discovered dozens of elements: gold, silver, oxygen, nitrogen, carbon. Each element was different. Different properties, different behaviors, but there seemed to be no connection between them. Some elements were metals, shiny, conducting electricity. Others were gases, invisible, floating in air. Some reacted violently with water, others did nothing at all. It was chaos, beautiful chaos, but chaos nonetheless. And the human mind seeks patterns. We need order, we need understanding. So scientists began asking a simple question: is there a pattern? Is there a hidden order in these elements? This question, this deep curiosity, is why the periodic table exists. Not because someone decided to make a chart, but because nature itself follows rules. And when we discover those rules, we can organize what we see. Think about it this way. If you know the alphabet, you can organize any word. If you know numbers, you can arrange them in order. The periodic table does the same thing for all of matter. It takes over 100 elements and arranges them so perfectly that you can predict how they will behave just by looking at their position. not magic. This is science at its most elegant. And tonight, you're going to understand how it all works. No rush, no pressure, just understanding. Slowly building, like dawn breaking over a quiet horizon. Take a breath. We have all the time that we need. Let's go back in time to the early 1800s. Chemistry was young, still finding its voice. And a German scientist named Johann Doberheiner noticed something curious. He was studying a group of three elements: lithium, sodium, potassium. All three were soft metals. All three reacted with water. But here's what fascinated him. When he arranged them by atomic weights, the middle element, sodium, had properties exactly in between the other two. Its atomic weight was almost the average of lithium and potassium. He called these triads. Group of three. He found more: chlorine, bromine, iodine, calcium, strontium, barium. Always the middle one was an average. This was the first hint, the first whisper of pattern. But he couldn't explain why. He just observed, and observation is where all science begins. Now, let's move forward a few decades to England, 1865. A chemist named John Newlands was working on the same puzzle. He arranged elements by increasing atomic weights, and he noticed every element had similar properties, like musical notes: do, re, mi, fa. He called it the law of octaves. Lithium was like sodium, beryllium was like magnesium. Every eighth element repeated the pattern. It was brilliant, but it had problems. After calcium, the pattern broke down. Newlands had discovered something real, but incomplete. The scientific community was skeptical. Some even mocked him. But he had seen the truth. Elements do repeat their properties. He just couldn't explain why or make it work for all elements. Now we come to the most important moment. Russia, 1869. A professor with wild hair and intense eyes, Dmitri Mendeleev. He was writing a chemistry textbook, and he wanted to organize the elements in a logical way. He wrote each element on a card: element name, atomic weight, properties, and then he started arranging them by atomic weights. but also by similar properties, and something magical happened when he arranged them in rows with similar elements in column. A pattern emerged, clear, undeniable. Elements in the same column behave the same way. Metals here, non-metals here. Reactive elements in one family, unreactive elements in another. But Mendeleev did something even bolder. When the pattern didn't fit, he left gaps, empty spaces. He said an element should be here, but we haven't discovered it yet. He even predicted what those undiscovered elements would be like, their properties, their atomic weights. People thought he was crazy. But then, years later, those elements were discovered. Gallium, scandium, germanium. Exactly where Mendeleev said they'd be, with exactly the properties he predicted. This was no longer a guess, this was understanding. He had discovered the periodic law. The properties of elements are periodic function of their atomic weights. In simple words, when you arrange elements by weight, their properties repeat in pattern. This table was not perfect. Some elements didn't quite fit. The atomic weight of iodine and tellurium seemed reversed. But the foundation was there. The order was real. And then came the 20th century. We discovered something Mendeleev didn't know of. Atoms have nucleus. Inside the nucleus, protons. And the number of protons is what really matters. Not atomic weights, atomic numbers. The number of protons, that's what determines an element's identity. Hydrogen has one proton, helium has two, carbon has 6, oxygen has 8. When we arranged elements by atomic numbers instead of atomic weights, everything clicked perfectly. No exceptions, no reversals, just pure, beautiful order. This is the modern periodic table, born from curiosity, shaped by observation, perfected by understanding, and now it's yours to explore. Take a moment, let this history settle in your mind. Scientists were not superhuman. They were curious, patient, willing to look at the same things everyone else saw, but think differently. And that's what you're doing now. Looking at the periodic table, not as a chart to memorize, but as a story of human understanding. Now, let's understand what we are actually looking at when you see A periodic table, what do you see? Rows, columns, numbers, letters. But each part has meaning. Let's break it down slowly, gently. First, the rows. The horizontal rows are called periods. There are 7 periods. Period 1 has just 2 elements, hydrogen and helium. Period 2 has 8 elements, lithium to neon. Period 3 also has 8, sodium to argon. Period 4 has 18 elements. Period 5 again has 18 elements. Period 6 has 32 elements. Period 7 has 32 elements again. You must be thinking, why do these numbers change? Because of how the electrons are arranged. Every electron shell has a natural limit. This limit exists because electrons need their own quiet space to move without disturbing each other. The rule 2n square tells us how much space each shell has, where n is the shell number. As we go farther from the nucleus, the space becomes larger, so more electrons can rest there peacefully. But don't worry about that now. Just know periods are rows, and as you go down, elements get heavier. More protons, more electrons, bigger atoms. Now, the columns. The vertical columns are called groups. There are 13 groups in the modern table, and here's the beautiful part. Elements in the same group behave similarly. They are family members. Group 1, the alkaline metals, lithium, sodium, potassium, all soft, all reactive with water. All want to lose one electron. Group 2, the alkaline earth metals, beryllium, magnesium, calcium. Harder than group 1, still reactive. Want to lose 2 electrons. Group 3 through 12, the transition metals. These are your common metals like iron, copper, silver, gold, zinc. Strong, conductive, often colorful. Group 13 through 16, a mix, some metals, some metalloids, some non-metals. Group 17, the halogens, fluorine, chlorine, bromine, iodine, extremely reactive non-metals. Want to gain 1 electron. Group 18, the noble gases, helium, neon, argon, krypton, xenon, almost completely unreactive. Don't want to gain or lose electrons at all. Stable, content, noble. Do you see the pattern? Groups tell you about behavior, periods tell you about size, and now let's talk about something called blocks. This is where electrons actually live, in regions around the nucleus. Imagine the atom as a building. Electrons live on different floors, and each floor has different rooms. The rooms are called orbitals. There are 4 types: S, P, D, and F. The S block, that is group 1 and group 2. Elements whose last electron enters an S orbital. 2 elements maximum in each period here. The P block, group 13 through 18. The elements whose electrons enters a P orbital. 6 elements in each period here. The D block, group 3 through 12. The transition metals. Last electron enters a D orbital. 10 elements in each period. The F block, the lanthanides and actinides. Those 2 rows pulled out at the bottom. Last electron enters an F orbital. 14 elements in each row. Why does this matter? Because the block tells you about the element's chemistry. S block elements are highly reactive. P block has variety: metals, non-metals, gases. D block metals are strong and versatile. F block elements are often radioactive and rare. For your exams, this matters. They'll ask, which block is this element in? What's the group number? What's the period? But more importantly, once you know these, you can predict properties. You don't need to memorize every element. You need to understand the pattern, and the pattern is already here. In the structure, 7 periods, 18 groups, 4 blocks. That's it. That's the framework. Everything else builds on this. Let your mind rest for a moment. Picture the table in your mind. Rows going across, columns going down, blocks forming regions. It's not random, it's organized. Like a well-designed city, each element has an address. And once you know the address, you know the neighborhood. And once you know the neighborhood, you know what to expect. This is the power of periodic table. Order from chaos. Understanding from observation. Breathe. We're doing well. No rush at all. Now, let's walk through this more carefully because understanding these concepts, truly understanding them, will make every chemistry question even more easier. Let's start with groups again. But this time, let's understand why elements in a group are similar. Take group 1, the alkaline metals: lithium, sodium, potassium, rubidium, cesium, francium. Why are they all similar? Because they all have one electron in their outermost shell. That outer electron is like a loose button on a coat, easy to remove. So, all these elements lose that one electron very easily. That's why they're all reactive. That's why they all form +1 ions: lithium, sodium, potassium. Same behavior because same outer electron configuration. This is the secret. Group number tells you about outer electrons, and outer electrons determine chemical behavior. Group 2, 2 outer electrons. Group 13, 3 outer electrons. Group 14, 4. Group 15, 5 outer electrons. Group 16, 6 outer electrons. Group 17, 7 outer electrons. Group 18, 8, except helium, which has 2, but it's stable. See the pattern? The group number is related to outer electrons. For main group elements, it's direct. For transition metals, it's more complex, but still related. Now, periods. Why do elements in the same period have different properties, even though they are in the same row? Because as you go across a period, you're adding protons to the nucleus and adding electrons to the same outer shell. But the outer shell doesn't change. Period 2 elements, outer electrons in the second shell. Period 3 elements, outer electrons in the third shell. As you go across, the nucleus gets stronger. More protons pulling on the same number of shells. So where atoms get smaller, more tightly held, and chemical properties change gradually from metallic to non-metallic, from reactive to unreactive. Left side metals, right side non-metals. middle is the transition zone. Every period follows this pattern. Now, let's think about the blocks again. S block. These are groups 1 and 2 plus hydrogen and helium. S orbitals are spherical, close to the nucleus. S block elements are often reactive. They want to lose those outer S electrons. P block, group 13 to 18. P orbitals are dumbbell shaped. A bit farther from the nucleus. P block is diverse. Metals like aluminium, metalloids like silicon, non-metals like nitrogen, oxygen, noble gases like neon. This block has everything. D block, the transition metals, group 3 to 12. D orbitals are more complex in shape. These elements are tough. They conduct heat and electricity well. They form colorful compounds. Iron is red when it rusts. Copper is blue in solution. Gold stays shiny forever. D block elements are the workhorses of industry. F block, the lanthanides and actinides, pulled out at the bottom to save space. F orbitals are even more complex. These elements are rare. Many are radioactive. Lanthanides are used in magnets, lasers. Actinides includes uranium and plutonium. You won't see them in daily life, but in nuclear chemistry, they're crucial. Now, here's something important that all of you have to consider. When they ask about electronic configuration, they're really asking which block. When they ask about valency, they're asking which group. When they ask about size, they're really asking which period. Everything connects. The table is not separate facts. It's one unified system. Once you see the connections, you stop memorizing. You start understanding, and understanding stays with you. Even while you sleep, especially while you sleep, because your brain processes patterns during rest. So, if you fall asleep listening to this, that's perfect. Your mind is still learning, still organizing, still making connections. Let's take a pause here. Breathe deeply. process. Now we come to something beautiful: periodic trends. These are patterns that repeat as you move through the table. And once you know these trends, you can predict properties without memorizing. Let's talk about the main trends slowly, calmly, one at a time. Atomic size, also called atomic radius. How big is the atom? As you go down a group, atoms are bigger. Why? Because you're adding electron shells. Each new period is a new floor in the building. More floors, taller building. So, lithium is smaller than sodium. Sodium is smaller than potassium. Makes sense. But as you go across a period, atoms get smaller. Wait, why? You are adding electrons to the same shell. But you are also adding protons to the nucleus. More protons, stronger pull. So the electrons are pulled closer. Tighter, smaller. So fluorine is smaller than oxygen. Oxygen is smaller than nitrogen. Right to left, bigger. Left to right, smaller. Downwards, bigger. Across, smaller. Ionization energy. This is the energy needed to remove an electron. How tightly is the electron held? As you go down a group, ionization energy decreases. Bigger atoms, outer electrons are farther from the nucleus, easier to move. As you go across a period, ionization energy increases. Smaller atoms, electrons held tighter, harder to remove. Noble gases have the highest ionization energy. They don't want to lose electrons. Alkaline metals have the lowest. They're ready to give electrons away. Electronegativity. This is how strongly an atom attracts electrons in a bond. Who wants electrons more? As you go down a group, electronegativity decreases. Bigger atoms, nucleus is farther from bonding electrons. Weaker pull. As you go across a period, electronegativity increases. Smaller atoms, nucleus is closer. Stronger pull. Fluorine is the most electronegative element. It wants electrons desperately. Friendship is the least. It barely cares. Metallic character. How metal-like is the element. Metals loses electrons easily. Non-metals gains electrons. As you go down a group, metallic character increases. Easier to lose electrons. More metallic. As you go across a period, metallic character decreases. Harder to lose electrons. Less metallic, more non-metallic. Top right, most non-metallic, fluorine, oxygen. Bottom left, most metallic, cesium, francium. Do you see? Everything connects. Size, effect, ionization energy. Ionization energy affects metallic character. Metallic character affects electronegativity. It's all one system. And for your exams, they will ask which element has the highest electronegativity in this period. You look right. Which has the largest atomic radius in the group? You look down. Which is more metallic, sodium or magnesium? Sodium. It's to the left. You don't need to memorize hundreds of values. You need to know the direction. Up and right. Smaller, higher ionization. More electronegative, less metallic. Down and left. Bigger, lower ionization. Less electronegative, more metallic. That's it. 4 trends, 2 directions, and suddenly the entire table makes sense. This is what I mean by understanding. This is why the periodic table is beautiful. It's not random numbers. It's a living pattern. And you are now part of that understanding. Close your eyes if you'd like. Picture the trends. Arrows moving across. Arrows moving down. Properties changing smoothly, predictably. You don't need to remember everything tonight. Just let it settle like snow falling on a quiet field. Gentle, gradual, real. Let's talk about why you're really here. You might be preparing for competitive examinations. Every single one test your understanding of the periodic table. Not just memorization, understanding as well. The periodic table is not just a chemistry topic, it's a thinking tool. When you understand the patterns, you can solve problems. you have never seen before. When you know why elements behave the way they do, you can answer questions without having seen them in your textbooks. This is what separates good students from great ones. Great students understand systems. Great students see connections. And the periodic table is the ultimate connection. It links atomic structure to chemical behavior. It links position to properties. It links theory to application. Master this table, and half of inorganic chemistry becomes easy. Coordination compounds, you'll know which metals work. Chemical bonding, you'll know which elements bond now. Acids and bases, you'll know which elements form which. Everything traces back to the periodic table. So, when you study, don't just memorize positions. Ask why. Why is fluorine so reactive? Because it's small and desperately wants one more electron to be stable. Why is gold so reactive? Because it's a transition metal with full or stable d orbitals and doesn't readily give up electrons. Why do noble gases not react? Because they already have full outer shells, perfect stability. Every question has an answer in the structure. And the more you ask why, the deeper your understanding becomes. This is active learning. This is what will carry you through your exams and through your life concepts. Not fear, not stress, just calm, confident understanding. And that's what this video is for. To give you that foundation, to build that confidence. One concept at a time. No rush, no pressure, just steady, reliable knowledge. You're doing beautifully. Now, let's talk about something fascinating. Sleep learning. You might have wondered, can I really learn while sleeping? The answer is not exactly. You can't learn new information while completely asleep. But here's what you can do. You can reinforce information you have already been exposed to. During sleep, your brain processes memories. It strengthens connections. It organizes what you learned while awake. This is called consolidation. So, when you listen to this video while falling asleep, your brain is reviewing, connecting, strengthening. The information you heard while awake becomes deeper, more stable, easier to recall. Here's how to use this video effectively. First, listen when you're fully awake. Sit with a notebook if you want. Pause When you need to think, absorb the concept. Second, listen. Maybe while studying other topics or while doing light review. Let it play in the background. Your mind will pick up pieces. Third, listen and beyond while sleeping. Let it play as you fall asleep. Don't worry about staying awake. Don't try to focus. Just let it wash over you. Your subconscious will do the rest. Many students have found this helpful, not as a replacement for active study, but as a supplement, a way to make their sleep time productive, a way to reduce anxiety. Because when you hear calm, accurate information, even in the background, it counters the fearful thoughts. What if I forget? What if I'm not ready? Instead, you hear steady knowledge, calm explanations, and your mind relaxes. Sleep learning isn't magic, it's just smart use of neuroscience. Your brain is always working, even at rest. So, give it good material, give it structured knowledge, give it calm repetition, and it will build understanding layer by layer. This video is designed for that. Slow pace, gentle repetition, clear structure. You can loop it all night if you want, or just play it as you fall asleep. There is no wrong way as long as you are relaxed, as long as you're not stressing. It's working. Trust the process. We're coming to the end now. And if you're still listening, thank you. Thank you for trusting the process. Thank you for giving your mind this gift of glow, deep learning. Let me leave you with a few final thoughts. The periodic table is more than a chart. It's a testament to human curiosity, to our desire to understand, to our ability to find order, even in the vastness of nature. Every element on that table was discovered by someone who refused to stop asking questions, who looked at the world and said, there must be more. And there was. You're part of that tradition now. Every time you ask why, every time you make a connection, you're continuing that journey. And your exams is not the end of your journey. It's just one checkpoint, one moment where you demonstrate what you understand. But the understanding itself that stays with you forever. So, as you rest tonight, know this. You're building something real. You're becoming someone who understands, not just someone who memorizes, someone who sees patterns, someone who thinks clearly, and that will serve you far beyond any exams. If you're using this video to sleep, let yourself drift now. Let the information settle. Let your breathe slow down. You don't need to hold onto anything. It's already inside you. Tomorrow, you'll wake up and a little more will be clear. A little more will make sense. That's how learning works. Not in sudden bursts, but in gentle accumulation. Day by day, night by night, you're doing beautifully. And this is just the beginning. Deep Sleep Global Academy will be here. More topics, more explanations, more support for your journey. But for now, rest, sleep well, dream of patterns, dream of understanding, and know that you're exactly where you need to be.